Remember that this example is the second part of a two-part example. We want to calculate the force on the pulley. In the first part we found that the tension in the string was 9.9307 newtons. The one that is at an angle we will resolve. We resolve in this direction and in this direction. We can see a Z angle, so this angle must be theta. So horizontally we have 9.9307 times the cosine of theta. And in this direction 9.9307 times the sine of theta. We can draw a vector triangle for the forces acting on the pulley. We have a horizontal force, a vertical force, and the resultant will be the third side of the vector triangle, and this is the angle alpha. In the first part of the example, we found cos theta was 4/5 and sin theta was 3/5. So we can work out the horizontal component of the force, 9.9307 multiplied by 4/5. This gives us 7.94456 newtons. Vertically we have this added to this. This gives us 15.88912 newtons. This is a right angle triangle, so to find the magnitude of R we can use Pythagoras' theorem, the square root of 7.94 and so on squared, plus 15.88 and so on squared. Calculating this gives 17.8 newtons, correct to three significant figures. We also want to give the direction of the force on the pulley, so we need to calculate the angle alpha. Alpha is going to be the inverse tangent of the opposite, which is 15.88 and so on, divided by the adjacent 17.944 and so on. And this gives us 63.4 degrees to three significant figures. Finally, we're told that after 1 second the string snaps. We want to find the speed of A when it hits the ground. We know that A initially begins to travel upwards. It accelerates upwards. We found that A was 0.1307 meters per second squared in the first part of the question. It travels with this acceleration for a period of 1 second. Clearly, A is going to then continue to travel up and then travel downwards until it hits the ground. We want the speed of A when it hits the ground. Let us consider the part of the motion until the string snaps. We can collect the information we need using SUVAT. We know that the particle starts from rest. The acceleration we calculated to be 0.1307 meters per second squared. The time is 1 second, and we need to know both the velocity and the distance that the particle has travelled upwards. To work out the velocity, we use v equals u plus at. We know that v is 0 plus 0.1307 times 1, so v is 0.1307 meters per second. Now for the distance travelled upwards, we can use s is ut plus a half at squared. This is going to be 0 plus a half of 0.1307 times 1 squared. So the distance travelled upwards is 0.06535 meters. So when the string snaps, the particle is travelling upwards at a speed of 0.1307 meters per second, and it has moved upwards by 0.06535 meters from its initial position 2 meters above the ground. Now consider the part of the journey after the string snaps. Collect the information using Suvat. During this part of the journey, the acceleration must be downwards at 9.8 meters per second squared. With no string, the particle is just moving under gravity. When the string snaps, the particle is above the ground, a distance of 2.06535 meters. I've taken this to be negative as I'm taking the upward direction to be positive. It's the 2 meters plus the distance it moved up before the string snapped. Upward is positive, so the acceleration will be negative. We know the object was moving upwards, and we calculated its speed as 0.1307 meters per second. We want the velocity. These four quantities are linked by v squared is u squared plus 2as. So v squared is going to be 0.1307 squared plus 2 times minus 9.8 times minus 2.06535. And we can calculate this and then take the square root to find v, which is 6.36 meters per second, correct to 3 significant figures.